So I'll share the screen and start the session now. Can you please confirm if you can see my screen? Can anyone confirm if they can see my screen? Can you confirm if you can view my screen? Okay, so could you please mute yourself? Yeah, so I'll start with the third live session of the NPTEL course, Basic Environmental Engineering and Pollution Abatement. Uh, uh, my name is Chaitra Borkar, a Ph.D. scholar from IIT Delhi, and this course is instructed by Professor Prasenjit Mondal from Department of Chemical Engineering, IIT Roorkee. So to reiterate, these sessions will take place every week on Saturday from 3 to 5 p.m. The live sessions link have already been shared with you, and these live sessions are recorded and will be made available to you through my YouTube channel. So let's start with the overview of lectures 11 to 14 for week 3. So lecture 11 was all about environmental quality and standards, and it dealt with ambient air quality and standards and water quality and standards. So ambient air quality and standards uh, in India are known as National Ambient Air Quality Standards, and they were established in 1991, and then they were revised by CPCB in 2009. And these are basically based on some criteria pollutants uh, such as SOx, NOx, carbon monoxide, lead, ammonia, particulate matter, and the pollutants can be of primary of two types. So primary pollutants and secondary pollutants. So primary pollutants which are directly emitted from the pollution source, and secondary pollutants are those which are created by these primary pollutants due to some reaction. So due to some ambient reaction. So the criteria pollutants are those on the basis of which on the basis of concentration of which we judge the quality of an ambient air. So these national ambient air quality standards are different for different regions as revised in 2009. So there are three types of region. So industrial region, residential rural region, and there are some sensitive regions in which the air quality needs to be maintained. And these air quality standards are different for different pollutants based on the method of how they are recorded, either by 24 hours concentration will be different and the yearly concentration will be different. Some pollutants are such that their hourly concentration needs to be monitored, or their 8-hour concentration needs to be monitored. So for a annual concentration recording, uh, uh, it is stipulated that it should take place 104 times a year. So as there are 52 weeks in a year, so twice a week, and these 2 days should have some equal interval between them. So these are the devices to monitor air quality, and these monitor the air quality in regular intervals. So water quality and standards is basically about the quality of water that we consume or that we use. So The water quality is based on the physical aspects. Physical aspects can be based on total solids. It can be based on the taste of your water, the odor of the water, the temperature and color of the water. The chemical aspects of that water will be the amount of oxygen dissolved, so DO, and biological oxygen demand, the chemical oxygen demand, the total organic carbons, as well as the hardness and the heavy metals present in the water. The biological aspects will be the aquatic organisms and the pathogens present in the water. So, a term called ion balance was discussed in lecture 11. So, basically, when you do the analysis of the ions present in the water, the sum of cations and anions should be equal for a given sample. Uh, and it should be less than the error percent, less than 5 error percent. If it is more than 5%, then there may be something wrong with the analysis that you've done. So, next criteria for judging water quality is hardness of the water. So, hardness is basically the ability of water to increase the amount of soap used. It is the ability of water to cause the soap scum, which is due to the presence of calcium and magnesium salts present in the water. So, it can cause scaling on pipes, as you can see in this figure. It can cause the valves to stick and leave stains on plumbing parts. So stains as well as scaling is present here. And the hardness is the sum total of the carbonate hardness, which are the temporary hardness, which can be removed by simple boiling of the water, and the non-carbonate hardness, which are temporary hardness. So the carbonate hardness is due to the presence of carbonate and bicarbonate salts, and the non-carbonate hardness can be due to the presence of such as sulfate salts or chloride salts. So there is also one more criteria to judge the water quality, which is based on the suspended solids. So you do not need any suspended solids in your clear water. So the clear water will not have any suspended solids. Based on the total dissolved solids, also you can judge the quality of water. So less than 1500 ppm of total dissolved solids in water is termed as fit for consumption. Uh, Certain RO companies also claim that they can control the total dissolved solids present in the water, and they can get it down up to 50 ppm of 50 to 10 ppm of total dissolved solids. So we move on to lecture 12. It was the continuation of environmental quality and standards. So they discussed about the designated best use class of surface water, and it is divided into 5 categories. So the first category, category A, is drinking water without any treatment, but with chlorination. The B type was for outdoor bathing. The C type was for drinking water, but with some treatment. D was for wildlife propagation, and E was for irrigation and industrial uses. So these are divided based upon the dissolved oxygen, the BOD, the pH of these waters, as well as some uh, some elements present in them. So one of them is solution absorption rate. So sodium absorption rate. So sodium, the presence of sodium in water. So if more of sodium is present, it can cause a reduction in permeability. It can cause reduction in hydraulic conductivity. Uh, it can cause the plugging of pores. So that's why we do not need more sodium in the water used for irrigation, so that the quality of soil is not degraded. So this is a criteria, sodium absorption rate, used for to check the suitability of water for irrigation. So another criteria is percent sodium. So percent sodium is basically the amount of sodium present uh, upon the total salts that are present in the water. Uh, Next is residual sodium carbonate. So if if too much of bicarbonate is present in the water, so it can cause the calcium magnesium carbonate salts to precipitate out. So which can increase the sodium absorption rate. So we want that percent RSC and percent Na should be as low as possible. So percent Na should be less than 60%, and percent RSC should be less than, I think, 0.25 or 0.25. And sodium absorption rate, the criteria for that is it should be less than 3. So then it is termed as fit for irrigation use. But in India, the sodium absorption rate is basically 26. Uh, um, Even though it is very high, but we keep it that way because sodium is being washed off because of the monsoon season. So there is a removal of sodium from the soils. So the drinking water quality standards were based on the taste, color, turbidity, and the pH of the water, and different metals that are present. So there are some certain standards and concentration limits up to which the uh, dissolved solids and the suspended solids, the heavy metals should be present in your drinking water. Heavy metals should be as less as possible because they are very harmful uh, for the living species. Uh, then there are some treated effluents quality standards. So the effluents emitted from the industry should have some standards before they are emitted into the environment. So the concentration should be limited as possible. Same goes for industrial effluent emissions. Next, the wastewater generation. So for to produce a certain useful product, how much water do you need? So the wastewater generation, the quantity of wastewater generated is also a limit is put on that. Then the load based and the concentration based standards also are stipulated so that amount of the useful product generated should emit as low as pollutants as possible. Then the noise pollution standards are also have been proposed based on the time of the day. So at night and day there will be different pollution noise pollution standards, as well as based on certain areas such as the commercial areas or the industrial areas or the residential areas or some sensitive areas where you need to keep as less noise as possible. Also the fuel quality. So because of the fuel combustion, a lot of pollutants are emitted into the environment. So we can control the pollution. We can control that pollution by controlling the quality of the fuel. So the fuel should be as less in sulfur content as possible. It should uh, it should have a and based on that also there are some vehicle emission norms. So for different vehicle types of vehicles such as CNG or such as diesel or gasoline vehicles, there are different vehicle norms. And these vehicle emission norms are based on the pollutants such as carbon monoxide, NOx, sulfur oxides, and particulate matters. So lecture 13 was about so these are the so up till now we saw that there are some quality standards which need to be upheld. So how do you measure those how do you measure the concentration of any pollutants in the environment or in the water or in the uh, air? So we need some instrumental techniques to measure that. So environmental analysis can be done through qualitative analysis, which basically gives the presence of any substance in that sample, and the quantitative analysis basically the amount of that substance present in that sample. So instrumental analysis comprises of electrochemical analysis based on the electrochemical properties of uh, material present in the sample. Chromatographic separation analysis based on the partitioning effect of these substances present. So, if you can separate it through chromatography, then spectrophotometric analysis is based on the how the when it is incident on a substance, how the interacts with that substance. It's the spectrophotometric analysis, and other techniques such as BET to give the surface area of a solid, and the XRD or TEM techniques can be used. So, firstly, the chromatographic analysis was discussed. So, in that gas chromatography and mass spectroscopy, and high pressure liquid chromatography were discussed, and the advantages and disadvantages, as well as the limitations to these techniques were discussed. Gas chromatography is basically the uh, most efficient and most accurate technique, uh, in the sense that it can use a less sample as possible and it can give very fast results. But the issue with gas chromatography, so the basic principle and working of these techniques were also discussed. So basic principle of chromatography is basically to separate the components based on the partitioning effect between the stationary phase and mobile phase. So stationary phase is mobile phase can be the gas that you have, and so the and you inject it with a mixture of helium. So a moving phase is the mobile phase, and stationary phase can be the walls of the column or the packing inside the column. So there can be two types of columns, for packed columns and the capillary types of column. So the gas chromatography components are divided into the injector, then the column is present, then there's a detector. This is for gas chromatography, and the whole setup is for gas chromatography, mass spectroscopy. So, based on the difference in the partition effect, so there are different materials present in the sample. So, those material will interact with the stationary phase and different phase, and will be retented accordingly on the stationary phase. So, based on the retention time of these substances on the stationary phase or in the column, you can find out what kind of a material is present in your sample. And GCMS is basically uh, when the separated uh, when these separated substances are converted into mass fragments by ionization. So then we can get the quantity of these substances present in the sample. Next is high pressure. The gas chromatography, the advantages is that it is efficient and accurate, but the disadvantages is that it cannot be. So it can be used for volatile substances which are thermally stable, but it cannot be used for non-volatile substances or substances which are highly reactive. But I mean, it will be difficult to measure them, and high and for substances which are thermally unstable. So for that we use high pressure liquid chromatography. So in that, the basic principle here is that instead of the use of gravitational force, we use a high pressure liquid of about 400 atm to use here in this type of chromatography. And this process basically eliminates the limitations of gas chromatography, in that it can be used for non-volatile substances as well as thermally unstable substances. But for volatile substances, one should go for gas chromatography only. The only limitation here for HPLC is the high cost. Next in the instrumental techniques was about the spectroscopic method. So we discussed in lecture 13 about the chromatographic methods. Now we discuss about the spectroscopic methods. So in that, firstly, UV visible spectroscopy was discussed. So this is the diagram for UV visible spectroscopy, and in that the UV as well as the visible light is used. So UV light ranges from about I think to 400 to 400 to 200 nanometers, and visible ranges from about 800 to 400 nanometers. And this method is based on Beer-Lambert's law. So the intensity, uh, so so uh, so the light incident on the substance, the as much as the light is absorbed by the substance, so it is directly proportional to the concentration of the substance. So much more the absorbance, more is the concentration. So, in this spectroscopic method of UV visible spectroscopy, we see that there's a light source and there's a monochromator for getting a beam of a single color. Then it is split into two beams in which to incident on reference cell and the sample cell, and then these are detected by photocells, and an alternating current is being produced because of the difference in the uh, current of these two detectors, and this current is amplified and then put into the analyzer so that you can judge the concentration of the substances present. Next is the Fourier transform infrared spectroscopy. So, for a substance, the infrared spectrum is a unique spectrum which we can generate. So, it is basically a fingerprint or a molecular fingerprint, the IR spectrum, and it's based on the types of bonds involved in your molecule. So, the Fourier transform infrared spectroscopy uses that basic principle and incidents the infrared radiations onto the sample, and it is consists of an interferogram which splits which has a beam splitter as well as a fixed mirror and a movable mirror, and it basically generates a collimated beam which is incident onto the sample, and then the IR spectrum is generated, which is analyzed by which is first detected by the detector and then analyzed in the computational device. So we begin with the sample problems for assignment 3. The first question is, which one is not a primary pollutant produced by the combustion of fuel? So can anybody give me the answer for this question? Which is not a primary pollutant? Can anybody give me the answer for this?
Smog.
Yes, correct.
Particle.
So, no, not particulate matter. I'll let you know the reason. So, carbon dioxide and carbon monoxide are produced by a direct combustion of carbonaceous matter. And particulate matter is basically, you can say, like soot is present, that is particulate matter. So, it can also be through direct combustion. As well as in diesel engines, we see because of the injection of air and injection of air, it can produce particulate matters. So yes, these first three options are primary pollutants, while smog. In case of smog, so smog is produced due to the reaction of NOx, which is generated, which is a primary pollutant, and the reaction between the organic carbon, volatile organic carbonates, and the NOx in the presence of sunlight produce smog. So yes, smog is the secondary pollutant. So the correct answer is smog. So the second question is, which one is not considered a physical parameter to measure water quality? So can anybody give me the answer for this as well?
Temperature,
Hardness,
Please.
hardness.
hardness.
Yes, correct. Hardness. Temperature, color, total dissolved solids are basically physical parameters. You can judge the quality of water, physical parameters which you can judge, which you can measure physically. Hardness, it's basically a chemical aspect. So the ions present in the water. So yes, it is a chemical aspect. So yes, hardness is the correct answer here. Next question, percentage error in a cation anion balance can be written as. So for percentage error, uh, can anybody give me the answer here as well? What should be the correct
Option
option?
one.
Yes,
Option A.
option. Yes, option A, correct. So the cation and anion balance should be less than 5%, and this is the correct relation for percent balance error. Yes. So the sum of cations minus the sum of anions upon the total sum. It should be less than 5%. So next question, which statement is not correct about water hardness? So what should be the correct answer here? What will be the correct answer here?
Maybe option A.
Not correct about water hardness.
Decreases the amount of soap needed.
Yes, correct. So hardness is basically it increases the amount of soap needed because it causes this scum to form, soap scum. So so because of that, the amount of soap needed increases. So the correct answer here should be the decreases the amount of soap. It is not correct about water hardness. Next question, if water has a higher amount of alkalinity in comparison to total hardness, then the value of non-carbonate hardness will be. This is a bit tricky, but if anybody can answer for this.
ये ऑप्शन 3 होगा.
No, no, no. Please think once more. If water has high amount of alkalinity, so alkalinity is greater than total hardness. So what will be the amount of non-carbonate hardness here? So I'll let you know the answer. It should be zero. So total hardness is sum of carbonate hardness and non-carbonate hardness. When alkalinity is less than total hardness, so carbonate hardness will be equal to alkalinity. When alkalinity is greater than total hardness, so the amount of non-carbonate hardness present in the water sample will be zero. So total hardness will be equal to carbonate hardness. Or I can write carbonate hardness will be equal to total hardness. So this is the relation. So next question, sodium adsorption rate is used to evaluate the suitability of water for irrigation and can be calculated as. So what will be the correct answer here?
Option 3.
Are the valency of calcium and magnesium correct here? Ca plus and Mg plus.
Option A.
Yes, option A. So the difference in all these options can be based on whether there is a factor of by 2 present 0.5 or whether there is a valency of the ions is correct or not. So yes, based on that, option first is correct. So Na has plus 1 valency and calcium and magnesium has plus 2 valencies and the square root divided by 2. So yes, the correct answer for sodium absorption rate ratio is the option 1. So question 7, spectrophotometric analysis based on the principle of, as we discussed, it is based on the principle of interaction of matter with light. So question 8, gas chromatography has become one of the most important tool because of. So as discussed earlier, gas chromatography is a simple technique, highly sensitive and the ability to effectively separate mixtures. So yes, all of the options are correct here. Next question, in FTIR analysis, the frequency range is measured as wave numbers. So wave numbers is inverse of the wavelength. Typically over the range of, as given in the definition, it is about 4,000 to, yeah, option 3, 4,000 to 400 centimeter inverse. Yes. So last question, find out the dissolved oxygen in milligram per liter in aerated water at 25 degrees Celsius in a treatment plant. So we have been given the Henry's constant, and for 1 molar of O2, the relation is 32 gram per liters, and the partial pressure of oxygen in the atmosphere is to be assumed as 0.21 atmosphere. So can anybody tell me here what will be the relation that will be used here to find out the dissolved oxygen? I had discussed it in live session 1. What relation will be used here? Can anybody tell me? So Henry's law is being used here. So suppose this is a water body and this is air. So O2 is present in this air. We know that it is about 21%, and the partial pressure is taken as 0.21 atm here because of that. And water has some oxygen also dissolved in it, but it's not that much soluble. But yes, it has some O2 dissolved in water as well. So there needs to be some equilibrium relation so that the amount of O2 in air is in equilibrium with the amount of O2 dissolved in water. So that equilibrium relation is Henry's law. So the concentration of O2 is equal to Henry's constant into the partial pressure of O2. So partial pressure will be in the uh, gaseous phase, and the concentration of O2 will be in the liquid phase. So Henry's law is the relation here. So we'll calculate the dissolved oxygen in that way. So Henry's constant is given to us as 1.26 into 10 to power minus 3 mole per atm, and we multiply that with 0.21 atmosphere, so we'll get molar. So it would be some value and then so this value will be suppose A. So then we multiply this A with uh, 32 gram per liter so as to get gram per liter, and to get into milligram you multiply by 1000. So this will be our answer. So the correct answer here is 8.467, and the calculation is given here. So 1.26 into 0.21 gives us around 2.646 10 to power minus 4 molars, and we then convert that molars into gram per liter by this relation. So we get about 8.4672 milligrams per liter. So this is the amount of oxygen in milligram per liter dissolved in the aerated water at 25 degrees Celsius, based on the Henry's constant given here. So are there any doubts up till here? Any doubts, or any doubts regarding whether assignment 1 or assignment 2? If you have any doubts, you can let me know. I'll discuss that as well.
Can you please explain how to construct that bar graph we make for hardness, in which we put different carbonate and bicarbonate and then calcium, magnesium, all.
Okay,
Uh,
okay, okay. So for that, just a minute. Huh? So yeah, so in the water sample there are different salts which are salts present, and based on that there are different ions are present. So it can be calcium, magnesium, sodium, potassium, and the anions will be sulfates and carbonates or bicarbonates or chlorides or something like that. So based on that anions and ions, so you get a basically reference. These are given in mg per liter or ppm concentration, correct? And then you convert into milli equivalent per liters based on their equivalent weight, correct? And so mg per liter to milli equivalent per liter. So this is the quantity that you need to focus on. So milli equivalent per liter. So based on that, you take one reference quantity. So suppose uh, you take, for example, sodium, or you can take the quantity which is present in the least amount. Suppose if Na plus is present, and it's present in the least amount in the water sample, so you take it as 1. Okay, I mean there will be some quantity in milli equivalent per liter, but if you divide, okay, so this is Na, so K, Ca, Mg, Cl minus, SO4 2 minus. So for Na, there is some X quantity, okay? So for Ca will be some Y quantity, Mg will have some Z quantity, it will have some W, or it will have some U quantity. So for Na, I'm talking about. So you take any quantity here which is the least in amount, and you take that quantity. So this will be another component here. So you can say that this is uh, concentration dash. Okay. So this will be x by x, and then this will be y by x, then this will be z by x, w by x. So you take one reference quantity, okay, and this will be w u by x. So you basically scale the other concentrations based on this one quantity, okay, and then you prepare. So This will come as 1, correct? And if this y is more than x, it will be more than 1. Let's say it is 2. So all this will be more because you have taken the least quantity, okay? So this can be 4. This can be, suppose, 3.5. Okay. So I'm just giving a sample calculation. It may not be correct, but the logic to create the bar graph is correct. Okay. So suppose Na is 1. So the Ca will be twice of that. Then Cl minus is 4 times of that. So this is 3. So it will be 4. Okay. And this is 3.5. I know the sum doesn't come out to be correct. So, but you get the idea. So basically, it's scaling based on one reference quantity. Did you get my logic?
Yes.
Okay. So yeah, that's how you generate the bar graph. But basically, you need to just get the quantities in milliequivalent per liters. But and I hope you know how to do that.
Yes, yes, I'm aware of that.
Okay. Any other doubt? Does anybody have?
Uh, I want to ask one more thing.
Mm-hmm.
Since in presentations a lot of values are given, so
Mm-hmm.
do we need to mug up all that for the exam?
I think not every value has needs to be mug up, but in the sense that if there are in one topic there are a few values which may be important, but not all the values need to be mug up. I don't think so. So the important which you feel important, and as well you can judge that by the questions asked in your assignments and the tutorials which are given. You can judge through that if the values are important or not. But not all the big tables and all that, you don't need to do that. But yes, in the sense that if there is a water quality standard, so based on that, what should be the criteria? So why the color changes, what are the components present in the water that changes the color or changes the odor or changes the turbidity, you need to know that. But apart from that, these big values which are present, I don't think we need to mark up. No.
Okay, thank you.
Yeah. Any other doubts related to whether assignment 1 or 2, you did not get anything? Any other doubt by anyone else, if anybody has any difficulties? So if there are no doubts you have, so I'll go ahead and close this session.
Thank you for the session.
Yeah, thank you.